Oh, not long till Sam gets back now. Can't wait. Hey, I know what I could do. There's that video that I made ages ago of the history of mine and Sam's friendship. Oh, I should give that a watch. What a good idea. It was a brilliant video. Here it is. Play.
But you don't have any viewers.
Oh no, Sam! Oh. Is that it? Oh, didn't realise it was that short, but... Alright, let's start the video then. Hello everyone, yes, it's the third instalment in the Parasite biology series, and today we're going to be talking about how parasites affect their hosts. Now obviously, parasites pose an extreme energetic cost to their hosts, but this can act as a huge selectional force. Right? Parasites can either feed directly off their hosts or destroy host tissues and affect the host that way. Now, as you'd expect, this can result in an immune response, which once again has an energetic cost, but can also pose a lot of harm to the host through immunopathology. Now, in the next 3 videos of the series, we're basically going to be dedicating that to how the immune system deals with parasites. Okay, so we're going to be covering that in a lot more detail later in the series. Oh, something to look forward to! Ah! Now, the harm caused by a particular parasite to its host can be intensity dependent, i.e. it can depend on how many you have. And this is the case for hookworms. Remember, we talked about them in the first video, particularly Nicata americanus, which bores into your foot and then gets into your intestinal system and sucks your blood. And they can take up to about 20 to 50 microliters of blood per day. This can result in a load of anemic effects, loss of iron from your system. Okay, so it can cause extreme problems. And this, especially when it infects children, will affect growth and also cognitive development. But like I say, the relative effects depends on the intensity of the infection. And in SDHs, so the soil transmitted helminths, has found that there's a negative relationship between infection intensity and cognitive development. So as intensity increases, cognitive development decreases. And it's been shown if by deworming, so wormers are people which you employ to get rid of all the worms from your system, whatever worm that may be. And this, in a study, has been shown to be linked with attendance to school, right? So the more deworming you have, the more you attend school and get better education and have a better life. Now, I guess the classic textbook example of how parasites affect the host can be seen in the Plasmodium parasite, or in other words, the deadliest organism on the planet, malaria, right? Of course, there's various different species of malaria parasite. The most common is Plasmodium falciparum. Okay, now I thought, because I think we've got a bit of time to spare in this series, so let's go over that malaria life cycle again. And you know my drawings are terrible, so I'm going to have a diagram on the board to explain everything to you, so let's go through it, shall we? Now the problem with life cycles is it's difficult to know where to start because it's all one big circle, but we're going to start at the very point where that annoying little mosquito bites you. And let me tell you, if it's infected with malaria, it's more than just annoying, okay? So, mosquito inserted proboscis, and in the saliva are those malaria parasites, more specifically the sporozoites of the malaria parasite. Okay, and these enter your system, and the first place they're going to go to is your liver. Now remember, just a brief recap, malaria is an apicomplexan. It is an apical complex which it uses to sort of force itself into your cells. More specifically in this case, the liver cells. At this point, a structure called a schizont is formed, which then leads to schizogamy, which releases merozoites. And where are those merozoites going to go? They're going to go for your red blood cells. And just like how they did with the liver cells, they're going to enter the red blood cells, rupture them, divide, more schizogamy going on. That'll create more merozoites, which go on to infect more red blood cells, then the cycle just goes round and round in circles. It's what's called the ring stage. So it looks like this endless cycles are unstoppable. But there comes a point when the malaria parasite begins to form gametes, if you like, gametocytes. Now, we must remember that the whole of this cycle pretty much is haploid. Okay, but there's a change in the type of cell that's produced in this division, which produces two gametocytes. Okay, so there's the microgametocyte and the macrogametocyte. And these are produced in the red blood cells, and when they're released, that's the point when that malaria parasite is hoping for another mosquito to come along and bite you and take up those micro and macrogametocytes. And from there, the cycle can continue. Now, we talked about in the first video how the mosquito is actually the definitive host for the malaria parasite. That's because it is there in the gut of the mosquito where fertilization takes place. So sexual reproduction, because the micro and the macro gametocytes fuse together to form the only diploid bit of the life cycle. And this is called an ookinete. And these ookinetes penetrate the epithelial layer of the gut. Now, many may die due to the innate immune system of the mosquito, but some will survive. So once it's out, it's now in the hemolymph of the mosquito. And at this point is where it turns into an oocyst. Okay, not an ookinete, an oocyst. And at this point, this is where sporogeny occurs. So it divides by meiosis, forming those sporozoites. So we've returned to the haploid stage of the life cycle. And then these will move into the salivary glands of the mosquito, and then the cycle can just carry on going round and round again, infecting and probably killing more and more people. Now, this erythrocytic cycle, so this is the cycle of, repeated rupture of red blood cells in your system, can create a lot of cell debris, because, there's a load of rubbish hanging around after that. This, of course, has an energetic cost, because it means more erythrocytes, red blood cells, have to be made to compensate for the loss of the ones that are being broken. Now, this is when we get to the point, okay? Now, we know red blood cells contain hemoglobin. It's one of the key compounds in red blood cells because it is that transports oxygen all around our bodies. Now, hemoglobin has a complicated chemical structure, but the important point is that it's made up of 4 globin molecules. The heme part comes from the iron that's also within the molecule. Okay, but it's the globin molecules that we're interested. So there are 2 alpha and there are 2 beta globin molecules. So that means one hemoglobin molecule can carry 4 molecules of oxygen, right? So they're extremely important. And infection of the malaria parasites will reduce the amount of hemoglobin in the body, obviously, because so many red blood cells are being ruptured. Now, the normal allele for hemoglobin is HbA. There's a mutant allele which is HbS, and this is caused by a single point mutation, right? So it's very small, but it has a massive effect. Now, this mutation, when you are homozygous for it, you have sickle cell anemia, which, as you may have heard of, cause huge deformations in red blood cell structure, causing coagulation in the body, loads of organ failure. It's probably not very good news if you have sickle cell anemia, I'm afraid. And more specifically, this is a mutation in the beta globin molecule, right? So when it's produced, transcription, translation, all that nonsense, they'll come together to produce this deformed or mutated hemoglobin. How many of those beta molecules are mutated depends on whether you have sickle cell disease or sickle cell trait. If you have sickle cell disease, that's bad news, right? If you have sickle cell trait, you're absolutely fine. So sickle cell trait, only one of the beta globin molecules is mutated. Here's here's the interesting bit. What does sickle cell anemia have to do with malaria? Right, so this phenotype is more common in sort of sub-Saharan Africa, and it occurs at polymorphic frequencies, and this is a classic case study for population geneticists, right? Because what we see is that areas where these genotypes are common are correlated with areas where there's high malaria infection. So why is that? That's because you're comparatively protected against malaria if you have sickle cell trait than if you didn't. Okay, so there's an advantage of having this mutated allele. That's because this mutation in the beta molecule is making the red blood cell less hospitable for the malaria parasite. Malaria infected cells seem to be cleared by the immune system more quickly if you have this beta globin mutation, right? If you have sickle cell trait. So therefore malaria has selected for this phenotype. So obviously the best outcome possible would be to be heterozygous, because if you're homozygous for sickle cell anemia, then you've got sickle cell anemia. Not very good news, right? If you don't have an allele of this mutated beta globin molecule at all, then you're at risk of getting malaria and dying that way, right? However, if you're heterozygous, so if you carry the sickle cell trait, if you're a carrier, then you've got the best of both worlds. Protected against malaria, haven't got sickle cell anemia. Way! Now you do get mutations in the alpha globin molecules. They're less common, but they still do happen. So here we've got a list of genotypes which would be phenotypically normal. Lead to phenotypically normal individuals. So you've got alpha alpha and alpha alpha. Well, obviously, right? So that's the perfect situation. Here you have a mutation in one allele, but then not in the other. So you've got minus alpha. That's also phenotypically normal because you're heterozygous for both alpha globin molecules. Okay, and here you're also phenotypically normal. If you have minus in one alpha globin, but then alpha alpha in the other one, then as long as you're homozygous in one, you won't get sickle cell anemia, or the equivalent, alpha thalassemia. So what we see is around the world, malaria has had the same selective effect. So that just shows what a massive selection pressure this little parasite is having, right? And it's been shown through extensive sequence analysis that these mutations have arisen independently in different parts of the world. So in Africa and India, the mutation in the beta globin molecule in most cases is in a different place. Okay? So this is convergent evolution, and it's just evolution in action, really. We talked about in the first video a little bit about Ascaris lumbricoides and its weird life cycle. Remember all that coughed up and then swallowed again business? Okay, now this was done in a study looking at the possibility of having wormy people. Right, we touched on this last time, right? So in this study, individuals were infected, right, and then fecal egg counts were collected, and then 2 years later they were infected again. And what was found was that individuals which had the most worms at the start were the same people who had the most worms when the second infection experiment took place 2 years later. Now, this could be down to behavioural effects, but also it's very strongly believed that there's a genetic link here. Right, now a pedigree analysis was conducted to look at the heritability of these phenotypes, and a h-squared value was calculated, which is a measure of heritability, and this gave a value of 40%. So that meant 40% of the worm variation that we saw within individuals can be explained by host genetics. Now that may not seem like much, but 40% for a h squared value is pretty damn good, actually. So this is pointing at the fact that wormy people do exist. This implies that helminths like Ascaris are having a strong selectional force on their hosts. Right, so specific portions of the genome were looked at, and it was narrowed down to about 6 quantitative gene loci. And these loci are involved in antibody production and complement cascades. Now that may not mean a lot to you, but we're going to be covering that next time. So whoa, more to look forward to. And these host genetic effects can also be down to T-cell differentiation. Oh, I got a bit chilly in here. I'm going to put my jumper on. Now I'm going to end the video talking about virulence. So these are the harmful qualities of the parasites which cause disease in the host. So this is very much an interaction phenotype. It depends very much on the features of the host and of the parasite itself. For example, if you have a big... In fact, let's draw it. Why not? Where's my pen? Okay, so this is going to be a very simple diagram, so I think I should be able to carry this one off, believe it or not. So we have a big host and a small host, right? And both hosts are infected with 2 nematode worms. Let's say there's the 2 nematode worms. As you can see, the parasite infection on the smaller host is likely to have a much greater virulence, right? Likewise, so that's how, physiology of the hosts can affect virulence. Let's say the hosts are the same this time. So those circles are going to be the same size, believe it or not. And then here we have a longer nematode, 2 longer nematodes in this one on the left. Well here, once again, the one on the left is going to have a greater virulence. So it very much depends on the host physiology, the host genetics, as we talked about with all those wormy people, going around. What a thought, walking around the streets there's loads of wormy people. And also the parasite's genetics. Now thinking about it, parasites should evolve to be avirulent, which seems a bit sort of paradoxical, really, doesn't it? Because you want, one, you want to keep your host alive so you can carry on using up its resources, but also you don't want to, generate that immune response which could potentially attack you as a parasite. Okay, so it pays to be avirulent. But clearly, this is not the case in many of the parasites which we see in everyday life today. And the explanation to this can be due to this sort of group selection argument. So this isn't natural selection on the individual level, this is selection as a group, right? But there are other arguments as well. Okay, so parasitic traits that affect virulence are often to do with the growth and reproductive stages of that parasite. Now, obviously, growth, reproduction, they result in a fitness benefit. So anything which increases growth and reproduction will be selected for by natural selection. Inadvertently, that means there's a selection for virulence traits, and it is because of this that virulence is maintained in the population. Now there's been various speculations on the effects of things like vaccinations against various diseases, because it's thought that vaccinations could produce more virulent parasites in the future. That's because by vaccinating someone, so allowing the host to survive through parasitic episodes, gives that parasite scope to evolve, and as a result become more virulent. And this can only be truly seen when we introduce that parasite, which has been infected a vaccinated population. If we introduce that into a population which hasn't been vaccinated, it is then we can really see an effect. Otherwise, we don't really notice it. Okay? So virulence, it's all about this trade-off between growth and fitness but at the same time, you don't really want to kill your host. Okay, so parasites face a whole load of dilemmas in their lives. And on that note, I'm going to leave it. Next time, we're going to have a nice little summary. It's going to be a more relaxed episode on the immune system, right? We all love the immune system. So, I'll see you then.